name is Ronnie Luss, and I'm going to talk to you about a work. It's joint with a very big team that we worked on to release this toolkit this past summer with researchers and software developers from IBM from Yorktown, which is one of our research facilities about 40 minutes north of here, India, and Argentina. So we titled this, One Explanation Does Not Fit All, about explainability for AI, because there's many different people with many different reasons for wanting explainability. So when we talk about a taxonomy, we're talking about the need to define different tools for explainability. Everyone has a different goal in mind, and I'm going to get into that. So the agenda for the talk, first I'm going to talk about why we need AI to be explainable. Then I'll spend some time talking more directly about the algorithms that were developed at IBM. And then I'm going to show a little bit of a tutorial on this toolkit that we released, which is called AI 360. Okay, so everyone knows that AI is becoming very abundant, used everywhere, many different disciplines, used by banks to determine credit limits. That's been in the news very recently. Employment, admission, it's used to predict things about retention, who to target for applicants even to college. For sentencing, it's used in parole guidelines, all over. These are very real-world applications, very real life, a lot at stake. So as AI has been used much more in all these different disciplines, computational resources have increased a lot over the past 20 years. A lot of new things can be done. And on applications we didn't think about back then, now we can achieve so-called 99% accuracy, and probably better on many applications. The question is, if you're actually using AI, and you're developing new tools in AI, how do you get people to actually use these AI tools? You say has 99% accuracy, that's really great, but there's still in society, I think, a lack of trust in using AI. You really need, in these real world applications, if you don't have that trust, even though it's 99% accurate, you're not going to use it. So this is a non-exhaustive list of what you might think of. What do we want AI to give us? What questions can we ask? Is it fair? Why did it make this decision? Is it accountable? Questions we ask of AI, questions we ask of many other things. And I'll say that a lot of these messages, Adi's talk just gave was very good, so I'm going to agree and say that a lot of this is the same message of what she was saying, that in AI we need a lot of responsibility. Everything that I'm talking about is not new. It's been in the news for a long time. Lots of different companies are using AI tools across many different things. The headline here, when a computer program keeps you in jail, about hey, AI was used in determining parole for people. And if you make mistakes, the consequences affect people's lives. So the quest for explainable AI is very real and a very necessary thing to look at. When we ask for explainable AI, the question is, what are we asking for? We're not the first person to ask this question. We're not the first person to say, what should we ask? So for example, the GDPR regulations that came out, they defined saying people are, what they should be given is the right to be provided with meaningful information about decisions that are given to them by these AI tools. What does meaningful mean? That's something we try to define. We're on our way, but it's certainly not a finished product. So how can we define what is meaningful? We ask, what can explainable AI give us, and what do we want to get out of it? So I'm going to go through a short list of a few of the things we're going to ask of it, and a few of the tools that we want to understand from AI in order to get people to trust it. So I'll start with simplification. We have a complicated network here, for example, and the task is deciding whether or not a piece of code is malware. So in some applications, someone came up with this very complicated neural network that a human looks at it, you can't understand what's going on. A couple engineers analyze what the output is, and they find out, well, what it's really doing is predicting that does this code have comments or not? Because evidently, people that write malware don't care much to document their code. Do we need a complicated neural network to classify using such intuition? So if we could explain what the model's doing, we can come up with simpler models. The next thing is debugging. So here we have a task of a self-driving car, and it slows down at the red light, but it doesn't stop. So we want to be able to explain, why is it not stopping? Why do we want to explain it? We don't want to get rid of self-driving cars. We want to be able to get this moving along. We want to be able to debug the program and figure out what's going on so we can get systems that work. The existence of confounders. So one thing we want to be able to get from explanation is to identify spurious correlations. So if you took a data set, medical data set, you could possibly come up with the intuition that pneumonia is indicative of someone not having diabetes. This comes up in a data set when people have pneumonia and you create your correlations. However, what it's missing is the fact that people who have pneumonia generally go to the hospital. When you get admitted to the hospital, everyone gets checked for diabetes, and most people don't have diabetes. So unless you know that people were in the hospital, you're going to think that just because you had pneumonia, you don't have diabetes, which is very, very much not true. So we need to explain why this decision is being made. A key thing that we just heard about in the last talk also, fairness. Is the decision system making a fair decision? What does fair mean? This is a whole topic for discussion, of course. But AI does need to be fair. I think we can all agree on that. Robustness and generalizability. Is a system making decisions based on the features it should be? So here you have a dog in the winter, maybe it's a wolf, and the question is it being predicted the correct species of wolf because of what it looks like or because of its environment? What's the correct features that it should be looking at? And we want to be able to understand that from the model as well. Okay, so this is the story so far. AI is everywhere. We need to explain it, and there's many reasons on why we want to explain it. So now let's talk about different types of ways you can explain models in AI. So the toolkit that I'm going to give a tutorial on is called AI X360 that we developed at IBM. It was released in July. It's open source. You can get it on GitHub. What I have at the top here are a bunch of different dimensions that we can classify different methods for explainability under. There's a bunch of different toolkits out there already, so we're just putting this to differentiate ourselves a little bit. For example, the Microsoft tool that Adi discussed. So it has some of the tools are the same, but the main thing in our toolbox from the beginning was that we only included homegrown IBM tools into it. And the hope to show some success is that people are going to also put their own tools into our toolkit. So the purpose of this is also part research and part for everyone to contribute and work together. So these dimensions of explainability, so the idea here is to create a taxonomy. So the idea, not one fits all. There's no explanation for one explanation for every problem, because there's many different dimensions to look at. So the first one we're going to consider in this taxonomy is directly interpretable versus post hoc interpretations. What this dimension means, you have a class of models that's already interpretable. Decision rules, trees, things that you can, as a human, look at and understand why is the model giving its prediction. So we have those types of models versus post hoc interpretation, where you have a very complicated model like a neural network, and the way we're going to explain it is using some type of surrogate or approximation, something simpler. For example, one of these directly interpretable models that approximates a complicated network, and we're going to get intuition out of that. At the next dimension, we're going to look at global versus local explainability. Global is where you are a person and you care about generally what's going on in the model, how it predicts across an entire distribution of data. Versus local, where you want to explain why is this model predicting this classification on a particular instance. And then the last dimension is static, where you're simply presenting the interpretation to the user versus a more visual interpretation where the user can interact with the interpretation that we call interactive. So here's the taxonomy. So at the top we have static versus interactive. AI X360 doesn't yet have any visual analytics, so we're only sticking with static. If we go to the next branch, data versus model. So we have explainability for data. So if you have complicated data that you don't understand and we want to be able to interpret the features, we have some tools for that. For example, dip VAE, which is in the toolbox. If we look on the other side, I'll focus on that, understanding models. For the next branch, we have local versus global tools. On the global side, we have, again, direct versus post hoc. One of the direct tools, BRCG, that was implemented at IBM is called Boolean rules via column generation. It's basically a rule list of, and then the post hoc is surrogates that you can use to explain a complicated model afterwards. So for example, we have a tool I'll discuss called ProfWay. If we look on the other side, local tools, we can look at post hoc versus self-explaining. And post hoc, what we have is a tool for looking at either samples or features. Samples meaning we're going to give an explanation for a data point based on looking at other data points in the data set even. Which data points, a group of data points is similar to this data point that give us some intuition. Versus features, where we're trying to answer questions such as, how can I change this data point in order to achieve a different classification? And what intuition do I get from that? So now I'll dive a little bit more into these tools. So we'll start with the directly global interpretable models. So these are the ones that we look at that as a human you can look at and understand what's going on. A decision tree or a rule list, you look at the top, and based on whatever the prediction is for your data point, you can trace down and figure out exactly what's going on. And of course, we can debate if this is really interpretable to a human, because if this tree goes down 1,000 lines, then maybe we have to use some other surrogate and try and approximate it with a shorter decision tree even, which we've done. So the tool in AI X360, one of them is called BRCG, the Boolean decision rules via column generation. And essentially, this is a rule list that is made of what are called DNF formulas, disjunctive normal form formulas, ors of and. So what that means, you get a rule that says, classify this as a 1 if A and B and C happen, or if X and Y and Z happens, or if D and E and F happens, and so forth. And so you just get a big rule list that you can look at and understand what's going on. A variant of this technique actually won last year in the NeurIPS 2018 FICO challenge, which was a credit challenge explaining why people were approved or denied on loans. Then another tool we have for the post hoc interpretation. For the post hoc interpretation, we're explaining a complicated network instead. And what we want to do is explain that with a surrogate. So we have our deep neural network, and on the right we can either use decision trees or simple curve fitting, or even a simpler neural network that maybe we can understand. You can use ensembles of these simple models to try and explain the deep neural network. And a tool in AI X360, this is dealing with the one called ProfWay. The idea here was to explain a complex neural network by transferring information to a simple model. So specifically, say that you're someone that's really fixed on using your decision tree. You're in manufacturing and you predict things using your simple decision tree. You don't want to use a complicated neural network even though it'll give you better accuracy. What we do here by using the complicated neural network is transfer information to improve the performance of your decision tree. So even though what you were using was one decision tree, we give you a new one that just performs better. So you don't still have to use the complicated network that you don't understand. And the goal there is also on some applications to try and improve the performance of the simple model to somewhat near what the complex model can do. And caveat to just mention, stuff like this has already been done. One topic called knowledge distillation, where from neural networks they transfer information by fitting a simple model to the predictions of the neural network. This is what knowledge distillation essentially does. And what we're doing is creating information transfer by taking a neural network. We extract information from different layers of the network. That's what these logistic probes are called. So say you cut off a network after 2 layers and you added a classifier after 2 layers. You get your prediction. We can extract information that way on how well the neural network is performing with only its first 2 layers, its first 3 layers, and so forth. And then we can extract that information to weight the data points on a simple model and improve it that way. So after post hoc global interpretations, now we're going to look at post hoc local interpretations. One of the more classic things that has been done are called saliency maps, which are very nice specifically for image data. So the idea with saliency maps is essentially you classify image. The goal here, again, let me just go back. Our goal is to explain why a classifier is outputting something. Whether or not that output is correct or not, that's not what I care about. I want to explain why it's saying what it's saying. If it gives a bad classification, I want to give an explanation why it's giving that bad classification so I can know it's not a good classifier. Maybe I can fix it. So here for the saliency maps, what it does is take the gradient of the classifier and evaluate that at the point. Essentially, what this says is, what is the relevant parts of the image towards the output of the classifier? And that's what you get from taking the gradient in this manner. So the saliency maps are on the bottom row, and it highlights, like for the first image on the left, where the boat is. Essentially, this is classifying what the image is, so it's highlighting the most important part of the image. The problem, I would say, with saliency maps is that afterwards a human needs to really look at that saliency map and understand what's going on. You can't just read that and get your explanation. So one of the things that we looked at was giving alternative types of explanations at a local level. And what we went with were contrastive explanations. So in contrastive explanations, we want to take a data point and its classifier. So here, the person in the upper left is classified as a young male and he's smiling. And we want to explain why this classifier says he's young, male, and smiling. And the way we're going to do that is by saying what attributes, minimal set of attributes, should I say, would we add to this person such that the classifier would classify him as something different. And so what that's called is the pertinent negative explanation. So for this instance, in that column on the bottom, if we add brown hair, makeup, and bangs to this young man, he would be classified as an old female who's still smiling. And one of the cool things is that we can also not just give out this application, we can modify the data point and show what that data point would look like with these extra attributes. So this is called the pertinent negative. That's one part of contrastive explanations. One part I'm not showing here is also called the pertinent positive, which would look at this young male smiling and say, what's the minimal sufficient attributes he needs to maintain so that he's still going to be predicted a young male smiling? So basically it's saying what are the attributes that the classifier is focused on that maintains him to be classified as such. Okay, so those are all the tools that I wanted to discuss so far. And before we get into the tutorial, I just want to reiterate what the message is here, that one explanation does not fit all. You have different stakeholders, everyone cares about something different. And there's the examples, there's not enough. Or sorry, there's too many. So for example, if you're a doctor and you're using AI to predict on an image that someone has cancer, how do you get someone to trust that? How do you get the doctor to trust to use this tool? So he's asking, why did you recommend me this treatment? That's his question from AI, because he's not going to go and use such a tool unless he really understands and trusts that tool. If you're applying for your loan and you were denied, you want to understand, well, why did it deny me? Why? Because you'd like to make changes to your application so that a year from now you can qualify for your mortgage or your car loan. Regulatory bodies, the government, what's their interest? Proving that the system doesn't discriminate. Why? Because hopefully they care about society and want to do the right thing. Then you have the AI systems builders, stakeholders, the developers, the engineers creating these tools. What do they want? They want to know, is the system performing well? Is it giving good accuracy? Is it doing all the other stuff and giving explainability as well, because their job is to give us good tools. So everyone has a different thing they need from explainability, and so we wanted to create this taxonomy to appeal to a large variety of stakeholders. Okay, so now I'm going to give a little tutorial about AX 360. I'm going to focus on two examples. One of them is that contrastive explanation example that I went into, and another will be the FICO example using several of the tools from AX 360, like the ones that won that competition last year. Okay, so you can download AX 360 on GitHub. It's an open source library. One of the nice things that we did and worked hard on was creating a lot of tutorials and example notebooks so people can dive right in, understand how to use it, and hopefully plug in their own tools. So we're going to go to the examples folder, but basically there's a few different things. In the AX 360 folder is all the algorithms, there's documentation. So if we go in the example folders, these are different types of algorithms that we have. Contrastive has two different types of methods for contrastive explanations. DipVAE was something I mentioned if you need to explain the features in a data set. So one nice application of that, for example, is if you're dealing with a data set that doesn't have attributes you understand. DipVAE is a tool to extract and transform to variables that you can get interpretations for. So then you're going to plug more interpretable features into your model. We have different metrics. ProfWay was one of the global post hoc examples that I showed you. ProtoDash is a tool for finding prototypes of a data set, of a sample point. IBM has the Boolean rule lists. And then Lime and Shape were, as you see 15 days ago, was recently implemented. But originally we started with our own IBM homegrown tools, and Lime and Shape are things that were not homegrown to us. But we want to build this using everyone's AI tools as well. We want to create a tool for everybody. Okay, so let's look at the first tutorial that I want to go over, explaining neural network decisions on data that have high-level attributes. So this is an example using contrastive explanations, and specifically for data that has predefined high-level attributes. So that data set that I showed you before with the images, this is called Celeb A. It's a facial images, and it has predefined high-level attributes, meaning it has attributes saying whether you're smiling, whether you're old, what color your eyebrows are, what color your hair is, are you wearing makeup, bangs, features about your nose, your ears, glasses. And for this tool, we need to have such high-level attributes. So actually in the paper we wrote about this, we have other examples where you don't have high-level attributes, but you can use that DipVAE tool to extract interpretable features. And then we can get contrastive explanations using those. So this is a tool, again, for getting pertinent positives and pertinent negatives. Okay, so what does the tool look like? Any other tool? We have a few open source libraries. Here we need TensorFlow. And then we have the AIX 360 tools. Specifically, we have wrappers for the different explainers. So you have a model that you have to give a wrapper to, and then we have explainer objects. So you can explain different types of models. And also for all these tutorials, we explain the public data sets that we're using, how you can download them, or even here we have tools that'll download it for you. So we start a TensorFlow session, we load the model to be explained. So again, this is about explaining a model, not about actually having an interpretable model. I have a model that is definitely not interpretable. It's a really large neural network, and my goal is to explain it somehow. And here we define explanations using contrastive explanations. So we wrap this model into the framework. We download a sample image. Here, we're going to plot him, and what does he look like? He's not young, he's not smiling, and it's a he. He's a male. So that's what the classifier actually says. Now, that's what this model predicts, and that's what he clearly looks like to us. But imagine that the classifier predicted he was a female and he's not smiling and he's young. We still want an explanation. Why is the model telling us that? And you would use this tool to give us answers to that question as well. Okay, at the top here, we create an explainer object. And as with all these explanation tools, you have different parameters. You can get an idea of what these parameters mean if you read the papers that are cited in the tutorials. We run the algorithm. So here it's loading models for black hair, for blonde hair, for brown hair. So this is a tool where I said we need high-level attributes, and we also need pre-trained classifiers on these attributes. Something to tell, does this image exhibit someone with black hair, with blonde hair, wearing lipstick, and so forth. We're going to use those classifiers to generate contrastive explanations. It runs the algorithm, eventually it finishes, and it's going to give us an output. The output, the pertinent negative explanation, is a male, smiling, and not young. So before he was not smiling, now it says he's smiling. And the explanation, why is he smiling? Because it added high cheekbones to the picture. So let's go back to the other picture. You see how his mouth is. Now it made him a little more smiley. And why? It says it added high cheekbones. This is what the algorithm learned by looking at all the attributes. And the nice thing is it changed the actual picture. So what's the actual contrastive explanation? Is that we would have predicted this person to be a male, not smiling, not young, unless we would add these high cheekbones, in which he would now be a male, smiling, and not young. That's our explanation. And this is done in plenty of places, like for predicting whether someone has the flu versus they have something else. A doctor will look at, okay, you have a fever, but you're not coughing. So that's the, if you were coughing, you'd be, perhaps you have pneumonia and not the flu. This is what we mean by contrastive explanations, and it's used all over the place. And there are articles that say this is the more intuitive way that humans actually process explanations. So this is the pertinent negative. There's also a pertinent positive in the tutorial, but I am going to skip that for now. So now we will look at the credit approval tutorial. So this is with the FICO data. And so there's 3 different stakeholders in this tutorial. The data scientist, who's providing the model, and he wants to know why it's giving the outputs it's given so that he can tweak it and make it a better model. He wants to trust it for himself. The loan officer, who is using the model, and he wants to know, he just denied an applicant, why is he denying this applicant? Can he see a group of applicants that's similar to this applicant that makes him understand why he's denying that applicant? And then you have the bank customer, who wants to know how can they change their application so they're approved next time. Usually someone that's approved doesn't want to know how they get denied. So this bank customer is going to use contrastive explanations. So we've already seen that, so I'm going to stick with the data scientist and the loan officer for now. Okay, so the data scientist here, there's different tools you can use in the AIX 360, Boolean rules, and a logistic rule regression model. I'm going to stick with the Boolean rules right now. So we load the data, and we print out, here's what the data looks like. So you have anonymized customers on the columns, and a sample of the different types of variables, the features of our applicants. External risk estimate is actually, the lower you are, the worse you are as an applicant, the more risky you are, for example. For Boolean rule lists, again, we're creating, if you remember before I said, we're creating ors of ands. So a rule that says X and Y and Z. So looking at those numbers before, we can't just make rules, so you have to binarize the data. So what that means is for each attribute, we create these new features. So a feature that says whether or not for your risk estimate, your value is less than or equal to 59. Another feature that says whether or not you're less than or equal to 63, and so forth. And also for the greater than, on the other side, is your risk estimate greater than 59, greater than 63. So binarize and create all these features on all the different inputs. Then we run the Boolean rule column generation, and we get our output at the bottom, which says, predict y equals 0 if any of the following rules are satisfied, otherwise y equals 1. y equals 0 says that you are a risky person, a bad applicant, and you're likely not to repay your loan. And what it says here, 2 different rules. If your external risk estimate is less than or equal to 75 and your number of satisfactory trades is less than or equal to 17, and another rule very similar, we should reject you. This classifier had something like 67 or 68% on the data set with just 2 rules. And so even with very complicated data, we can learn very simple rules, explainable rules that you can look at and understand the output of your model. We have the loan officer now. So the loan officer is the one who is telling you whether you are approved or denied. And he doesn't like denying people. So he wants to know when he denies someone, what is it that caused him to deny? He wants to know he made the right choice. So again, we import the models that we need. We use the AI 360 tools that we need. Here it's the ProtoDash tool and the HELOC data set. We load our data. A few things that I'm skipping: processing, normalizing the data for this tool, defining and training a neural network classifier. So we want to explain the classifier. This classifier is just going to stand for something that this is the loan approval model, we're assuming. And we want to explain why is this neural net classifier approving and denying people. So we obtain similar samples as explanations for a HELOC applicant predicted as good here. So the chosen sample was 8. This person was predicted good at the bottom, and it has what his sample probabilities would be. We run the ProtoDash explainer, which is a wrapper for AIX 360 around the tools developed in a paper cited in the tutorial. The optimal solution has been found after a while. And then we display similar users. So we look at these users. Now, what does this loan officer do? He can look at these 5 users that are prototypes. Now, let me be clear. These are 5 previous applicants that went through this model and were either approved or accepted. Here, they were approved. And that's in contrast to the explanation tool before. We generated a new sample point for the contrastive explanation. So here, we look at 5 people that were previously approved, and he's trying to figure out why was my current applicant, who's similar to this group, what does he have in common? And most of the prototypes have no debt. So he falls into a class of people that have no debt, and that's why he was most likely seen not risky and approved. This is how the loan officer can use this tool. Okay, so that's it for the tutorial that I wanted to give. I'm going to say just a few more words on all these toolkits. So what I've talked about today is AI Explainability 360. We've released some other tools related to trust as well. Adversarial Robustness 360. Last year, AI Fairness 360. And one of the next things that we want to work on is Causal Inference 360. And the goal is to support a community of users and contributors, not just IBM. We want everyone to be able to download and contribute to these tools, so we hope that we've made it easy for people to plug in their tools themselves. And lastly, this again, I said in the beginning, this was developed by many people, not just myself, more than 15 researchers, engineers, across at least 3 continents. So thank you.
Hi, so I had one question was, there's one popular technique I'm aware of called LIME or K-LIME. I think it was also in your Git repo. Where would you put that in your taxonomy? Like, which definition would you point that
LIME is a local, I would call that a local interpretability tool. So LIME is looking at specific instances. So you have a complicated model, and it's effectively trying to get local using linear approximations locally to explain a specific data point.
Okay.
So if you look, the only problem, LIME is used by a lot of people. The only problem is that when you look at data points that are somewhat close, you might get different explanations. So there's some work to say, how can we use something like LIME? But also, it's a little weird to give different explanations for data points that are very similar. So some type of LIME-like tool that'll give explanations near each other. But I would say it's a local tool.
Okay. One more question, sorry.
Yeah.
what are your thoughts on using stuff like dimension reductionality to give you like a sense of which were the key properties that were looked at and why?
Yeah, I would say that that is widely used and necessary. So, for example, the dip VAE, it's not clear how many, you have a large dimensional data set that you don't understand, and we want to get new features. So there, the thing is, it's called disentangled representations. So disentangled meaning you want representations that the features are somewhat orthogonal to each other, so you can get some type of interpretation. There's not much overlap between them. And so with high dimensional data, there's definitely a need for variable reduction if you want to, especially if you're trying to explain the data itself.